Ugh. All right. I'm hoping this works. Okay, so we're trying number 36 here, which is another one of these bug moving across the graph paper problems. So bug first is noticed at 3, 4. So let me figure out how to record these data points. Okay, so we'll say here that bug initially at 3, 4. So that'd be like time 0. And then after 2 seconds, it's at 9, 8. And then after 4 seconds, it's at 15. And it says it's moving linearly at a constant speed, so we should assume that it's going to keep this pattern going. So the first question is, where is it after 6 seconds? Okay. If you were to draw a picture of this, you should be able to see a pattern. 3, 4 is where it starts. And then it goes to 9, 8, so 4, 5, 6, 7, 8, 9, and then there's 4, 5, 6, 7, 8. And if you kind of calculate, it takes 2 seconds to go there, and that's 1, 2, 3, 4, 5, 6 across, 1, 2, 4 up. And you can repeat that to get to the next 2 seconds later. So if you went over 1, 2, 3, 4, 5, 6, that actually gets you to 15, and another 4 up gets you to 12. So this one's 15. That's 2 more seconds to get there. And this is at t equals 0, t equals 2, 4, number 6, 4 there. Okay. So notice every 2 seconds, you move 6 right and 4 up. Okay, well that also means every 1 second, every single second, then you're going 3 right and 2 up. Just kind of keep it in the back of your mind here, okay? So we want to figure out where is it after 6 seconds. Now I know you can just count over 6 and up another 4, but what I want to do is kind of help you start thinking a different way about these problems. So really the key is, well, you know that over 6, up 4 is the 2 second kind of triangle. So the 1 second triangle would be over 3, up 2. And you're just dividing by 2 there. So what are we looking for? 6 seconds. 6 second triangle would just be a bigger version of this one. So 6 seconds, this is not the scale anymore. But this one would be 3 times 6 down here, so that'd be 18 across. And 2 times 6 is 12 up. And so what we've got now is, if you think about where your starting point was, 3, 4, you can add 18 to the x and 12 to the y and figure out where your ending point is. So at 6 seconds, the bug is at, and we started at 3 and had to add 18 to the x. We started at 4 for the y and had that 12. This ends up being 21 plus 16, which I do realize there are easier ways of getting that for the problem. Okay, so what I want to look at now is at 9 seconds. Okay, so this one's for 6 seconds. The next question was, I think 9, right? Yeah, 6 seconds. Okay, so to do that, well, you could start out with this 2 second thing again, but we already have the 1 second version, so I'm just going to put that here. 1 second, 3, 2. I want 9 seconds. 9 seconds. So I'm going to multiply everything by 3 to get this similar triangle over here. So, whoops, 9 times 3 is 27. 9 times 2 is 18. And my starting point was 3, 4. So if I go over 3, so this is at 9 seconds. Bug is at. So I was at 3, and I went over 27. And then I was at 4 for the y, and I went up 18. So I ended up at 32. Or the bug did, anyway. Okay. All right. So the reason that I wanted you to think of it this way is because I think that makes the t seconds a little bit easier to answer because we have the 1 second triangle again. So it took, if for every second we went right 3 and up 2. So if I multiply by t, I've got a t second triangle here where I'm starting at 3, 4, and I'm moving to the right t times this. So 3t instead of just 3, and 2t instead of just 2. And my endpoint, so t seconds, the bug, that, and then it's 3 plus, so the x was originally 3, and then I moved 3t to the right, and the y was originally 4, and I moved 2t up. So that's where I am at t seconds. So that's how you do part A. Right? If you wanted to check if your formula was good, try plugging in 9 seconds, 6 seconds, 4 seconds, and 2 seconds for t. If you plugged in a 9, you're going to get 3022. If you plugged in a 6, you're going to get 2116. If you plugged in t equals 4 into that equation down here, or this formula down here, you would get 15 and 12. So those are quick ways to check if your formula makes any sense or not. So then part B says, is there any time that the bug is equidistant from the axes, the x and y axes? Okay, so equidistant from the axes means whatever distance, here, let me write it down here. If I want to be equidistant from the axes, then like this point right here, the distance straight down to this have to be equal to the distance over there. If you think about it, kind of means that the x and y coordinates better be the same. Because if you pick a random point, like 1, 2, 3, 4, 1, 2, 4, 2, the distance from a point like that to this axis would be the y value, and the distance to this axis would be the x value. If I want them to be the same, well, then those two values in the coordinates have to be the same too. So x and y have to be the same. So we want x and y coordinates to be equal. This is for part B. Okay. Well, we know the x and y coordinates are always in this form. 3 plus 3t, 4 plus 2t. So the bug is equidistant from the x and y axes when the bug's x coordinate equals the bug's y coordinate. And if you solve this out, you get t equals 1. So it happens at 1 second, and the way to figure out where it happens is to plug it in to the bug's location kind of formula here. So you're plugging in t equals 1. 4 times 1. That is a 6, which is good, because that would be 6 units from the y-axis, 6 units from the x-axis. That's really all I wanted you to figure out. I realized that you may have stumbled upon 6, 6, just as you were sort of working out this problem. If you actually just go over 3 up 2, which probably a lot of you did, you realize that point is 6, 6. But in a problem where that doesn't occur so naturally, this is sort of the method you want to come up with. Where's the bug at any time? And then set up that any time so that the x's and y's are equal to each other to find that equidistant from the axes point. Now there's a subtle other point that occurs where it's equidistant from both axes. And I don't expect you guys to have come up with this. But if you go backwards in time, somewhere over here, the bug's distance to this axis is the same as the bug's distance to this axis. Ooh, let me undo that. There. So this distance right here equals this distance right here. That occurs when the x value of this point, when this value is the negative of that value, like at the point like -1, +1. So it actually occurs, also when the x coordinate equals the negative y coordinate. That's way more subtle, I think, to figure out. But you could do it. Oops, about that. Could do it by setting up the x coordinate of the bug, setting it equal to the negative y coordinate of the bug. And if you work this out a little bit, let's see, it's 3 plus 3t equals -4 minus 2t. And so that'll be 5t -7. T -7 over 5, which ends up being -1.4 seconds. -1.4 seconds means 1.4 seconds before you started watching, before you noticed the bug. It was right here. Right? So that was 1.4 seconds earlier. And to get the coordinates for -1.4 seconds, you can just plug in -1.4 here and here. So it's at 3 plus 3t and 4 plus 2t. And that ends up coming out to -1.2. No, -1.2, +1. Yeah. And if you check that, yeah, that should make sense that that's 1.2 units away from each axis. Now, again, I'm okay if you didn't come up with this one. That's a little bit tricky, and it requires you to assume that the bug was moving in the same pattern before you were watching it too. Okay, I hope that helps a little bit and gives you some insight into how these problems have been working with the T's. I do strongly encourage you to sort of think of it in terms of this idea, get the 1 second rule so that you can get the any second rule. Okay, that's going to come in handy the further we get into this year. Okay, I hope that helps a little, and I'll see you soon.